So we have studied the divergence theorem and see that it is the higher dimensional generalization of the Green formula and the Gauss formula. Green and Gauss you have studied in calculus 2, in the course calculus 2, and we also we also introduce some application of the divergence theorem. In particular, the Archimedes floatage law, principle of floatage, and the very useful integral identities, the Green's identities, and the integration by part formula. Okay. Now we have not proved the divergence theorem. The divergence theorem, in the statement of the divergence theorem, we need to use the integral of an continuous function over higher dimensional surface. The space dimension is not 3 anymore. It can be higher. Okay, so before prove the divergence theorem, we need to study higher dimensional surface. Okay. So this part is not difficult. Higher dimensional surface integral. And we will use this to prove some special case of the change of variable formula for multiple integral. Now, U is an n-1 dimensional region. By a region, we mean Jordan. By a region, we means an opened set, open the Jordan domain. Open the Jordan domain. Okay, so this is a region. And a parametric surface. A parametric surface is an injective C1 map denoted by X from U to n-dimensional space. Such that not all injective C1 map can be called a parametric surface. It need to satisfy additional conditions. These conditions are: first one, the derivative are bounded. Xj, because X is a vector valued function, X has n components. Xj is the jth components. So this dixj is precisely dxj dxi dui. The independent variable is u. Okay, for all the I and the j, the derivative of xj with respect to ui are all bounded. Bounded means that the supplement, when you go over the whole region, capital U, the set of numbers is a bounded set. Okay, so this symbolically it can be written by the supplement is finite. Okay, and also another condition is that the rank of this Jacobian matrix here is n-1. This is an n-1 matrix. Because this matrix I will write here dx1 du1. Maybe I will not write here. I will make some space for writing other materials. I write here dx1 du1 dx1 du2, dx1 du n minus 1. Because u is n minus 1 dimensional, u only has n minus 1 components. Then dx2 du1, dx2 du2, dx2 du n minus 1. Finally, dxn du1, dxn du2, dxn du n minus 1. So this matrix is just this matrix. This is the x prime u. That is our x prime u. Okay. So this is a parametric surface. Okay. Parametric surface is an injective C1 map, continuously differentiable map from n minus 1 dimensional region to n-dimensional space, such that the derivative or the partial derivative of all the components of x are bounded function in the open set U. Region is open set. And also the Jacobian matrix has maximal rank, because the Jacobian matrix, that is x prime u, that is dxj over dui. This is an n by n minus 1 matrix. Its maximum rank is n minus 1. So we require that this matrix, the rank of this matrix is n minus 1 for any u in the region U. Okay, so this is the parametric surface. When n is 3, this reduces to the surface we studied previously. So this is simply a generalization of our previous definition. Okay. Now, a subset of Rn is called a smooth surface. It is called the smooth first surface if it is the image of some parametric surface. If S is the image of U for some parametric surface X. Okay, the image of a parametric surface is called surface. So parametric surface is a map, but the surface is a subset of Rn, has a beautiful shape. It is in some sense smooth. Okay. So such a parametrization, such a parametric surface is called the parametrization of the surface S. Okay, because every smooth surface is the image of some parametric surface. Then this parametric surface is called the parametrization of the geometric surface. Okay, and in this case we write as, we use this notation to indicate that the map X is a parametrization of our smooth surface S. Okay. So in our study of differential calculus, we also know that we also get this result. Maybe some of you forgot the result, but you can go to check our lecture notes. Okay. If S, the surface S, has a parametrization given by the map X, then this vector the last one is minus 1 n plus 1 x1 xn minus 1. u1 un minus 1. This vector is a normal vector of S at the point. Okay, this is a fact we proved previously. Here, all the components are Jacobian determinant. So the first component is the Jacobian determinant of x2, x3, xn, which is back to u1, u2, un minus 1. And the second component here is minus the Jacobian determinants of x1, x3, xn, which is back to u1, un minus 1. So the sign positive, negative switch alternative. Okay, positive sign and negative sign are alternatives. Okay, so this is the normal vector. Normal vector. And our condition of the parametric surface, we know that the rank of dxj dui is n minus 1. This means at least one of ni. These coordinates of the vector n could not be 0 for everyone. At least one of them is non-zero, because this rank is n minus 1. So this matrix here has an n minus 1 determinant contained in this matrix, not 0. For example, if the first n minus 1 row, the determinant corresponding to the first n minus 1 row is not 0, then that means the last component is not 0. Okay, so from this aspect, we know that at least one of the ni is non-zero. Therefore, this n is a non-zero. N is non-zero vector. N is non-zero. Okay, and then we also know that for the three-dimensional case, if n is 3, then the rank of x the rank is n minus 1 is 3. Rank of x prime u is 2. That is n minus 1. It's equivalent to d u1 x cross d maybe xu1 cross xu2 not 0. These are equivalent, as you can check. Okay, so this condition in our definition of a parametric surface, the condition that this rank is n minus 1 is a generalization for the case when n equal to 3, the requirement that Ru cross Rv is not 0. The reason is this. Of course, the previous R will be replaced by our vector, our x. We use x to in the place of our previous R, and then u1, u2 is the uv there. Okay, so because of a higher dimension, you do not have a cross product. So we use the matrix. Okay, and for the three-dimensional case, when n equal to 3, we have defined the surface integral. Fx yz d sigma to be the parametric domain f ruv, then ru cross rv du dv. Okay, But as we have mentioned, the RU cross RV is precisely the vector n given here. RU cross RV is dyz, the Jacobian determinant of this zx uv and xy duv. Okay, this is precisely our capital N given here. This is precisely our capital N. Okay, the negative sign, you might argue why you have a negative sign here. Negative sign is used to make the order of the x1, x3. X1, x3 in the three-dimensional case is x and z, but here in our formula you write zx here. If you write this by xz, you will have a negative sign. Okay, so the n given there for n-dimensional, the capital N given there for n-dimensional is a natural generalization of the normal vector RU cross RV we used before. So from this, it is natural to define the surface integral of a continuous function over the surface S, similar to this definition for n equal to 3, for the case n equal to 3. Okay, so we will define the surface integral. So if f is a continuous function over the surface S, we defined fx d sigma. This is called the surface integral of f, or the integral of f over the surface S. We defined this to be u fx u nu du. Okay, we use the n-1 dimensional multiple integral to define the surface integral of a continuous function over a surface in n-dimensional space. Okay, this definition, you can compare this definition for the two-dimensional case. F you can make some comparison. Here is a double integral here, because n is 3, n-1 is 2, and okay, and these two are the same. These two are similar. Simply replacing the point on the surface by its parametrization, by its representation by parameters from the parametric domain. Okay. Of course, our u here has n-1 coordinates, and here the capital NU is the normal vector, and the RU cross RV is also a normal vector determined by the parametrization. And as we see that when n equal to 3, the capital NU is precisely this cross product. Okay, so this definition for surface integral is precisely the generalization of the surface integral in R3 we defined and studied previously. Okay, now we have an important issue to investigate. That is, we defined the surface integral using a parametrization of the surface, that is x. Okay, but a surface could have more than one parametrization. If you change another, if you use the other parametrization, can you have, that is, the problem is that if y is another parametrization of S, can we have, yes, can we have this result? Can we have this? Here the n tilde is the normal vector given by the parametrization y similar to this one. Okay, here our n tilde, if you give another parametrization y, the corresponding capital N will be denoted by n tilde. Okay, so can this be true? If this is true, then our definition of surface integral is okay. But if this is not true, then our definition of surface integral is problematic. Okay, because the right hand side, the surface integral should not depend on the parametrization. But if the right hand side is different for different parametrization, then this definition is not valid. Okay, but similar to the case we studied in our previous study of the surface integral of 2-dimension surfaces in R3, we also have this problem, and we solve this problem using the change of variable formula for double integral. Okay, then this is our method to solve this question. And we know that the change of variable formula, the n-dimensional change of variable formula are denoted by CVF n. Okay, when n equal to 1, that is one-dimensional integral. In the single variable calculus, we know that for one-dimensional integral, the change of variable formula is true. Now we assume that the change of variable formula is true for n-1 dimensional. So first, n equal to 1, this is true. Second, suppose n-1 is true. n-1 is true. Maybe I will write in this way. CVF, change of variable formula for n-1 is true. We assume that n-1 is true. When the n-1 dimensional, if the n-1 dimensional change of variable formula is true, then we can prove that this is equal. Changing parametrization of the surface does not affect the value of the integral. Okay, then this means that our definition of the surface integral is valid. To ensure the definition of a surface integral to be valid, we need the n-1 dimensional change of variable formula, and we assume that this is true. Once this is true, we can define a surface integral over surface in Rn, in n-dimensional space. Then we should establish the divergence theorem, and then we use the divergence theorem to prove that the change of variable formula is true for n-dimensional. So suppose this is true. This is true. We have surface integral. Then we have divergence theorem. Maybe. Then we will obtain the n-dimensional change of variable formula. Okay, so n equal to 1, change of variable formula is true. Then if n equal to n-1, the change of variable formula is true, we will conclude that the n-dimensional change of variable formula is also true. Therefore, by the induction, mathematical induction, we know that the change of variable formula is true in all dimensions. This is our idea to prove the change of variable formula. And in this procedure, we also establish the theory of surface integral over higher dimensional surface, and prove the divergence theorem. Okay.